Welcome to everybody. Today we will start with addressing the regulation task for robot manipulator in the joint space. We will see a number of control laws from the simplest one to the more sophisticated, and we will also analyze their properties. Before doing this, we need to introduce and briefly discuss a number of stability definition criteria that will be used for proving the correctness of our control design. Then we will first address the case of robots in the absence of gravity, and we will introduce the so-called PD control in the joint space, which is, I would say, a basic result. Later on, we will introduce gravity, and we will see a number of ways for dealing with that. In conclusion, we make a few short remarks on this simple control law, and we suggest how to introduce this concept within industrial controllers. So, let's start with an introduction to stability. In particular, we roughly specify stability for a system, but in fact, we should refer to the equilibrium states of a dynamic system. So let's start with the definition of which are the states of equilibrium for a robot. We start from the dynamic model. We use the Euler-Lagrange approach, and we introduce some state representation. You could introduce any state representation. The most convenient one is using the generalized coordinate q and the generalized velocity q dot. So when you write down the equation in the state space format, you have a system of 2n nonlinear first order differential equation with a drift terms which is called f of x and a forcing term depending on the input torques. We are neglecting for the time being dissipative effect, but this could be introduced without any problem on the left-hand side and move to the left-hand side of the differential equation. Now there are two types of equilibrium in this context. The unforced equilibria are those for the robot left to itself, so when there's no command being applied, u equal to 0. In this case, the right-hand side becomes only the drift term f of x, so we need to find all state xe such that they zeros the drift term. And if we look at the structure, internal structure of the drift term, we see that this implies, in every case, that x2 should be equal to 0. So at the equilibrium, at any equilibrium of the robot, the second components of the state, so the velocities, should be 0. And this is typical of mechanical systems. When we plug in this into the second part of the drift term, then we will have that the colorless and centrifugal term vanishes. The inertia matrix, the inverse of the inertia matrix, is indeed non-singular. So setting this to 0 is equivalent to setting to 0 the gravity terms, which means that unforced equilibria are those, only those, that zeros the gravity term, so where the gravity is balanced by the structure. When we move to forced equilibria, we introduce an input, and this input may be taken in the form of a state feedback. This is the most general form. So we write u equal u of x, and then we zero the right-hand side of our state equation so that we don't move from that state, so x dot is equal to 0. And again, looking at the internal structure of f and capital G, we recognize that, again, velocity should be 0 in order to be in equilibrium, while the lower part, for the same reason, because we have the C vanishing, the Coriolis and centrifugal term vanishing, and the other terms pre-multiplied by the inverse of the inertia metric, which can be eliminated when we are setting this to 0, imposes that the control law, whatever control law we are using at the equilibrium, should exactly balance the gravity at the desired target configuration. So this is a very important condition, and we summarize it again in this sense. All equilibrium state of a mechanical system have zero velocity, so x2 is equal to 0, so q dot is equal to 0. And for our robots, at the equilibrium, joint torques provided by the control law must balance gravity. So this is a requirement that we would like to check every time we propose a new control law for our system. Now, let's be more general. Let's consider dynamic system in the form x dot equal f of x. This includes the previous cases, both unforced system, but typically also the forced system, forced by a feedback control law of the form u equal u of x. So when we plug in this, we have a new function f of x on the right hand side. Now the equilibria are such that f of x of e is equal to 0. Now sometimes we can rewrite the differential equation to let the error with respect to the desired equilibrium appear. In that case, the state becomes as the first component with a q minus q desired minus actual q, so the equilibrium will be xe equals 0. The first definition that we introduced of an equilibrium, so first we find the equilibrium of the system and then we ask ourselves if they share some nice property. The first basic property is stability. From a mathematical point of view, stability is defined in the way it is written on this slide, but essentially we have stability when small perturbation introduced to the system, for instance in the form of moving out from the equilibrium, will lead to small effect. So this is a very general statement, and one way of writing this is saying that no matter how you choose a parameter epsilon, there exists another parameter which is a function of what you have chosen, so a delta of E, such that if your initial state at time t0, this can be typically chosen as t0 equals 0 as the initial time of your experiment. So whatever initial state x of t0 you're choosing, which is not farther than delta epsilon from the equilibrium that you are studying, then all trajectories starting from that initial state will remain within the epsilon bound, and this for any future time. We will look at this in more detail in the next slide with an example, with a graphical example. There's another stronger definition and property that we would like to achieve, namely asymptotic stability of this equilibrium. Asymptotic stability occurs when you have already stability, so you have the previous situation, so no matter how you perturb the locally initial state, you will remain confined in the vicinity of the equilibrium. But in addition, there exists actually another parameter, delta, such that when you start not farther than delta from the equilibrium, then not only you will remain confined in a neighborhood of the equilibrium state, but your trajectory will converge to the desired equilibrium as time goes by. Now, all this property, in particular asymptotic stability, may also become global, which is exactly the same definition above, but you don't say that there exists a delta, but whatever delta you're using, even very large, so even starting far from the equilibrium, but indeed finite, you will converge to the equilibrium XE. Now, all these definitions are particular definition let's say, concept that we are associating to the fact that small initial perturbation, small perturbation of your system will not have large effect. Indeed, when this happens, when small perturbation produce large effect, not necessarily unlimited, but large effect that cannot be bounded a priori, then you say that your system is unstable. All this stability, instability, and asymptotic stability definition should be intended in the sense of Lyapunov. So you may also have systems in which your trajectory converges to the equilibrium without having the stability property. So without being able to limit the trajectory within a fixed neighborhood depending on the initial condition. But we will always refer to this definition of stability. So let's use the blackboard. If I were in the classroom, I would use the blackboard. Since I'm using slide remotely, I will have now a whiteboard, and I will use this term for a few following slides. So let's give a graphical representation of stability and then of asymptotic stability. So we have an equilibrium point Xc in a state. This is a planar system, so there are only two coordinates, but you can imagine that you can generalize this in an n-dimensional space. Just for visual representation, we are working in R2. So Xe is an equilibrium for our system. It means that if we start from Xe, we remain in Xe. This is the definition of equilibrium. Now, what does the definition of stability say? No matter how you choose a neighbor of your equilibrium point, a neighbor of size epsilon, so a circle, a sphere, or an hypersphere in n dimension, then you can find, so exists another neighbor, typically smaller than the previous one, with a radius delta epsilon, and this radius depends on the choice that you have done in the first step. Such that if you start, no matter where you start with your initial state, inside the smaller neighborhood, so when x of t0 minus x of e in norm is less than delta epsilon, then what happens? That no matter what you do, your trajectory will remain confined in the larger neighbor of size epsilon for every future time. In this case, you say that the equilibrium state is stable. In robotics, simple stability is not really of interest. It would mean that if your task is to go from one initial point to another point in your state space, so from one configuration, let's say at rest, to a desired configuration at rest, if you only have the stability property with your control law, then you will remain in the vicinity, but you will never get to the destination. And this is indeed not what we would like to have. So we would like to have asymptotic stability, which means, in the sense of Lyapunov, that we have the above properties, plus we have another stronger property. Namely, that there exists another parameter, positive radius delta, so around the equilibrium point of interest, such that if we start within this neighborhood, so with the norm of the distance to the equilibrium less than delta, what happens? Well, we will move around the equilibrium. Since we have stability as a premise, we will not exceed some larger neighbor, so I'm expressly showing a trajectory that exceeds in a transient the delta neighbors, but this is the neighbor for asymptotic stability. But the good point is that all this trajectory, no matter where we start within the neighbor of radius delta, will eventually converge to the equilibrium point as time goes by. Now, there's a limitation in this, because we may wait forever. I mean, as time goes by, means that we cannot have a prediction of how close we will be to the equilibrium when a fixed amount of time has passed. So there is another definition, very useful in fact, of exponential stability, which solves this problem from a practical point of view. So you have exponential stability, you don't need any premises for this. If there exists three positive number, delta, which define the locality of this property, so how close you should start from the equilibrium xe, and then two other parameters c and lambda, such that the error in future times, for all future times, will be bounded by the initial error and by an exponential function which is converging to zero with a exponential rate lambda, and then with a factor c that may correct things. You may think that c is just 1, but sometimes you would like to have a different value here. C should be, in any case, positive. So what does it mean, this? That not only we are converging, so not only we have asymptotic stability, we have a bound, so we have automatically also stability in the sense of Lyapunov. So this requirement is no longer necessary. But we can bound the trajectory with an exponential that is going to zero. So, from a practical point of view, we have an estimate of the time needed to approximately converge. Let's consider the case of c equal 1. Now, just studying the exponential function, we see that if we wait 3 times the time constant associated to the exponential rate, which is just the inverse of the factor lambda, so time constant tau is 1 over lambda, if we wait 3 times this time constant, then no matter what was the initial error, this is going to be reduced to 5% of its initial value. So we are practically close to the equilibrium, and we can give a quantitative estimate. Indeed, this is at most reduced down to 5%, possibly even more. So exponential stability is a stronger property of asymptotic stability. You may have an equilibrium which is shown to be asymptotically stable, but not exponentially stable. And the vice versa is instead true. If you have exponential stability, indeed you have also asymptotic stability. Typically, exponential stability is a local property only, so you cannot consider arbitrary finite large delta. So you could prove that you have a maximum finite radius under which you can have exponential stability, and you call this domain of attraction. In fact, you can have also a domain of attraction for asymptotic stability, but in this case it is more important to be able to define this domain of attraction. Unfortunately, for nonlinear system, general nonlinear system, this domain of attraction, so where local exponential stability holds, is quite hard to be estimated. Now there's yet another definition, the last one, which is practical stability, so even stronger more practical than the previous one, which is formally correct. But as you know, since exponential go to zero only for t going to infinity, you extract nonetheless some information on the rate of convergence. Now, practical stability is referred not to an equilibrium, but to a generic set. So you say that there exists a time which depends on where you start and which is the set that is your target, such that if you wait a finite amount of time, so starting from the initial time t0, you wait this capital T seconds, let's say, from there on, the trajectory will be confined to this set. So in practice, you know that you will be in this set infinite time. Now this is also, it's a property that is also called ultimate uniform boundedness of your trajectories, and it's very important in robust control. We have already mentioned what is robust control, so it's a design of a control law that enables to tolerate perturbation, restricting the degradation of your performance to by a defined amount, which is exactly the set in which you will converge in finite time. However, we will not use this concept if we are not dealing with robust control. So, after this definition, let's make this consideration. Okay, definitions are nice, but how can we show if they hold? So we need some analysis, and in particular we need criterion that guarantee, at least from a sufficient point of view, that this definition, these properties hold. So let's take again our whiteboard and look at a generic nonlinear system. This is not a robot, not even a simple single link. It's just a nonlinear system, unforced. So there's no command on the right hand side. x1 dot equal 1 minus x1 cube, and x2 dot equal x1 minus x2 square. So this is a system that lives in R2. So we would like to ask ourselves first, which are the equilibria? Are there equilibria? So are there states such that the right hand side of this differential equation is equal to 0? Well, there are two, in fact. You can easily see from the first one that you can have x1 equal 1 as the unique solution to this f of x e equal to 0. And when you plug this into the second equation, so x1 should be equal to 1, and now for x2 you can have two choices, either x2 equal 1 or x2 equal minus 1. So there are two equilibria for this nonlinear system, which we label with a prime or a double prime. Now we would like to say if this equilibria shares some stability or asymptotic stability or instability property. So what should we do? The question is to assess the presence of asymptotic stability of an equilibrium, of one of these two equilibrium and then of the other. Do we need to compute all system trajectories for this nonlinear system, meaning we should start from any initial state xt0 and then move this initial state in the surrounding of the equilibrium? Well, this is indeed impossible, and the answer is no in general. Okay, but in this particular two-dimensional case, we may, for instance, use MATLAB and draw the flow of the trajectory. This picture is made in the following way. The two black points are the equilibria. You see it's 1, 1 on top, and 1 minus 1 at the bottom, and for any other point, so state in the surrounding, I limited this to a certain square, there's an arrow drawn, and this arrow is exactly the vector field, so the evaluation of the right-hand side of the differential equation. So if you take any point there, you evaluate 1 minus xu cube and x1 minus x2 square, and you have a vector, and this vector is represented in a scaled format, indeed, in this picture. So if you do this, and of course you cannot do this in general, but for this simple system you can do this, now you can pick an initial state, for instance the green one, and follow the flow, which is the trajectory, the solution of the differential equation that you have considered. And you see that if you follow the flow, you will get eventually to the equilibrium xe prime. Now if you take another point, you can repeat this, and so on and so on. Of course you can have a picture from these vectors where the trajectory will converge. For instance, if you take a point very close to the second equilibrium, you will see that you will deviate and converge to the first one. And it's easy to convince yourself that the first equilibrium is asymptotically stable, the second one is not. So, what should we do in general? Can we repeat this type of analysis? Indeed not. So, Lyapunov theory of stability helps us in making conclusions if some criteria will be satisfied. And in particular, we may be able, no matter how large is the dimension of our state space, now I'm considering Rn or any other differential manifold of dimension n, basically we look at the scalar function of the state, so just one function, and we evaluate the evolution of this function over time based on the trajectory of the system. Now, we use the trajectory of the system implicitly as solution of the differential equation. So the differential equation of our system are being used in evaluating the time derivative of this scalar function. And this is basically the art of Lyapunov stability analysis. I say that it's an art, it's not an algorithm, because such a scalar function should be found. There are some converse properties that say if your system is stable or asymptotically stable, such a function exists. But finding that function in order to prove the reverse, so that some equilibrium or the whole system, because the system has only one equilibrium, so we just say the system is stable, asymptotically stable, or exponentially stable, and so on. So let's see what are these criteria. First of all, we introduce a function which is a Lyapunov candidate. This is a function which vanishes, so it's zero at the equilibrium of interest and is positive everywhere else. We call this a positive definite function. So a function that zeros at the equilibrium and otherwise is always strictly positive. And we will call this a Lyapunov candidate. Now, how do we build such function? Well, typically you use quadratic function. This is always true for systems with linear dynamics, not our robots, unfortunately, unless we are in very special cases. For instance, you have a quadratic function with a P matrix inside, and then the error between the current state x and the equilibrium xe. Now, if you look at this, if you have the P matrix is automatically, can be taken automatically as a symmetric matrix, and it should be a positive definite matrix in order that this qualifies as a Lyapunov candidate. And the level surfaces of this function will be in general ellipsoid. Now, another consideration that we make is that this function may also be a local candidate only. So not for all x different from xe, we have that this function is positive, but only in a neighborhood of the equilibrium. Then we have a local analysis indeed. If we are able to use a Lyapunov candidate that is positive everywhere except at the equilibrium, then it is likely that the conclusion that we make could be global as well. Now, with this in mind, with this candidate in mind, there are a number of sufficient conditions associated to the properties that we have introduced so far. The first sufficient condition is for stability. So if you find, if you find a candidate, Lyapunov candidate function V, and its time derivative evaluated along the trajectory of the system x dot equal f of x is non-positive, so it's negative or zero, so you have a negative semi-definite derivative function f v dot, then this is sufficient to conclude stability of your equilibrium. There's a stronger property, again a sufficient condition. If there exists a candidate function v such that its time derivative evaluated along the trajectory of the system is strictly negative, so you have a negative definite function as you had a positive definite function as candidate, you have a negative definite function as derivative of this candidate, then you have asymptotic stability. Of course, these are only sufficient conditions, in the sense that if you pick a function which is a Lyapunov candidate and you don't have such nice properties for its derivative, then you cannot conclude anything about stability or instability of presence of asymptotic stability or not. Okay? In this sense, it's just a sufficient condition. There's also a sufficient condition of instability, because if you find a candidate, a Lyapunov candidate, so a positive definite function, and you evaluate its time derivative along the trajectory, and you find that it is positive, then you can conclude that the equilibrium is unstable. Of course, in the condition you don't see the equilibrium point xe, the equilibrium point is in the Lyapunov candidate itself. So in this sense, we conclude about stability, asymptotic stability of instability of a specific equilibrium xe. There are more conditions, because the issue of stability has been analyzed by Lyapunov. It was a mathematician of the 2 centuries ago, but then further investigated by Lifshitz, Poincaré, Lassalle, and other mathematicians. So there's another condition, the sufficient condition for practical stability or ultimate uniformly bounded stability to a set, which essentially says that there exists a candidate and we can define level sets for this function, and then if the derivative is negative along the trajectory outside this level set, then we have stability, practical stability to this set. This set should be a level set for function, for the candidate function v. And the definition is given there. However, we forget for the time being this, because we will not use this in our lecture today, and in fact this is a condition that is used only when dealing with robust control. However, the second result, it's a theorem by Lassalle, which is very important, which adds something to the stability condition of Lyapunov. So suppose that we have a candidate, so a positive definite function v, such that its time derivative is non-positive, so it's negative or zero, along the trajectory of our system. As at this point, Lyapunov can conclude only that the equilibrium is stable. However, Lassalle says something more, because it says that the system trajectories will asymptotically converge to a specific set, which is an invariant set. Namely, if we start inside the set M, we will remain in this set M, which is the largest invariant set, so it's this largest set that we can find with this property contained in the set of states that zeros the time derivative of the Lyapunov candidate. So the picture is the following. We have a candidate positive definite, V positive and 0 only at the equilibrium xc. We compute, we evaluate the time derivative v dot along the trajectory, and we find that the sign of this derivative is negative or 0. Then we look at the states where f dot is 0, and Lassalle theorem says that we converge to the largest invariant set, which is contained in this set of state at 0, the derivative. So there's a nice, this is the definition of invariance. So there's a nice corollary. Suppose that this largest invariant set contains only one state, which is the equilibrium. Then, by the combination of Lyapunov and the Lassalle theorem, we conclude about asymptotic stability of the equilibrium. So only if this largest invariant set is made only of one point, namely the equilibrium point, then this equilibrium is asymptotically stable. So let's give an idea of how you perform Lyapunov analysis. Again, we take the whiteboard and consider a particular system. Now getting closer to some robotic system, although this is just a mechanical system, an oscillating pendulum, unforced, so passive, made by a concentrated mass n at the end of a link of length L. So we neglect the linked mass, we assume that there's a payload at the end of this link, which is heavy enough to include also the mass of the link. So the equation in this case is the following. You have an inertia term, so a mass at the distance L from its rotating point has inertia m times L squared, and this inertia is multiplying the acceleration of the angle of this pendulum. We consider also the presence of some viscous friction, so we have an additional term with a coefficient, positive coefficient b times the velocity of oscillation, and then this pendulum is under gravity, so we have a mass at distance L from its pivoting axis, the acceleration, the gravity acceleration g0, which is positive, and this is multiplied by the sine of theta. And of course there is no actuation, so on the right hand side we have simple z. Now we can rewrite this system into the form of x dot equal f of x if we use theta and theta dot as state coordinates. So we have the derivative of the first state is equal to the second one, so x1 dot is equal to x2, and the derivative of the second state is the acceleration t double dot, which we isolate from the previous equation. So we can write on the right hand side minus, we can simplify, we can divide everything by ml square, and in fact there's a missing factor at the end, so minus bx2 should be minus b over ml square times x2. But it makes no big difference, you can redefine this as a b prime, it's still possible. And of course, this pendulum has two equilibria. if you compute this equilibrium on the right hand side, so the velocity should be 0, and then sine of x1 should be 0, and this occurs, so this is sine of theta 0, this occurs either when theta is equal 0, so the lower equilibrium of the pendulum, or when theta is pi, so the upper equilibrium of the pendulum. Now consider just the lower equilibrium for the time being, and you can write now the flow of the differential equation. Again, we have two coordinates, so we can represent this in the plane. The two axes are now theta and theta dot, or d theta, written in MATLAB. This is the so-called phase plane, when you have that one coordinate and the derivative of this coordinate are represented in the plane. And the equilibrium is at the origin, so when theta is equal to 0 and theta dot is equal to 0. And you can see for a range that goes between minus pi and plus pi for theta, and some predefined interval, minus 3 and plus 3 for the velocities, you can find a flow of vectors, so a vector fields which are associated to the left-hand side, to the right-hand side of the differential equation x dot equal f of x. Now, how do you study? I mean, you can tell from this flow that probably you have asymptotic stability here, but let's use the Lyapunov machinery. Consider a Lyapunov function. How do we look for a Lyapunov function? Well, very often for mechanical system we use energy concept. This is also true for electrical system. We can use energy also in this concept. Energy is a ubiquitous function. So let's consider as Lyapunov candidate the total energy of the system. So the sum of the kinetic energy, 1/2 ml squared theta dot square, plus potential energy due to the gravity. This is written with an additional constant term, so that this second part is always positive, and is 0 only when cosine of theta is equal to plus 1, so when theta is equal to 0, so at the equilibrium. So at the equilibrium state, this function is 0 because the velocity is 0 and cosine of theta is 0. Otherwise, it is always positive by construction. So it's a good candidate. So we have this property. Now we can represent on the phase plane the level set of this particular function. You see they are ellipsoid. There are only few ellipsoid represented for a discrete number of level sets. And if we would look at the value of v getting smaller and smaller but still positive, we would trace ellipsoid which gets closer to xe equals 0, to the equilibrium, oriented in the way we have. So this is a good candidate. At least it's a candidate, so it's positive. It's a positive definite function, and it's 0 only at the equilibrium. So let's look at its time derivative. So we have to make the time derivative of this function. This function is not an explicit function of time, but it's a function of time in the sense that the variable theta and theta dot are a function of time themselves. So we use the chain rule. We take the derivative with respect to theta, and then of theta with respect to time, so theta dot, and the derivative of theta dot with respect to time, that gives us theta double dot. So, to make a long story short, we take this derivative. The first term gives 2 theta dot times theta double dot, and the 2 simplify with a factor 1/2 outside. So we have theta dot ml squared theta double dot. And if we do the same, there's a constant term which vanishes, and then we have a minus mlg0 cosine theta. So we take the derivative with respect to theta, and this gives minus sine theta, which cancel the minus sign, and then of theta with respect to time, and we have the theta dot that we factor out. Now, this is just the time derivative, but we have to evaluate this time derivative along the trajectory of our system. So along time, let's say, variable that satisfy the dynamic equation of our system. So which satisfy ml squared theta double dot plus b theta dot plus mlg0 sine of theta equal to 0. So we can replace from the equation on the top, for instance, ml square, well, the 2 out of the 3 terms. So this is equal to minus b theta dot, which is brought to the right-hand side. So the whole simplifies into minus b theta dot square. And this, because the friction coefficient is positive, this is a negative semi-definite function. Pretty nice at this stage. So we can conclude from the first criterion, the sufficient condition of Lyapunov, that the equilibrium Xe is stable. So we will not, if we start close to it, we will not wander around the pendulum will not start rotating in a wild sense. But in fact, we know something more. Because of the presence of friction, we know that eventually the oscillation will vanish and we end up in being at the lower equilibrium. So the first condition of stability is not enough for making our conclusions, and we would rather expect asymptotic stability. Okay. But the second condition for asymptotic stability of Lyapunov is not satisfied, because in this case V dot can be equal to 0 also when theta is not at theta 0, because in fact its derivative is not depending on theta, it's only depending on theta dot. So we will use LaSalle. And LaSalle is very powerful, because what does it say? It says, okay, we will converge under this condition to the maximum invariant set contained in the set where V dot is equal to 0. Now, V dot is equal to 0 if and only if the velocity is 0. So we will certainly converge to a set where a set of state where the velocity is equal to 0. So let's see, since this set should be invariant, let's see what happens when theta dot is equal to 0. So let's look at our original equation and plug in theta dot equals 0, because we know that we will converge to a set of state where this happens. Now, in this case, the dynamic equation when theta dot is equal to 0 become ml squared theta double dot plus mlg0 sine of theta equals 0. You can see that you can eliminate ml square, and again there's a factor L missing dividing G0 in this case. Too many errors, it's in this new slide in fact. But anyway, the conclusion is the same. So when theta dot is equal to 0, we see that the acceleration will be minus, in fact, G0 over L sine of theta, and this is different from 0 unless theta is equal to 0, for instance, so in our equilibrium, which means that we cannot converge to a set of state with theta dot equals 0 and theta different from 0, because otherwise we would have a positive acceleration or a negative acceleration, and this set of state would not be invariant, because with a acceleration which is different from 0, we will move out the set where theta dot is equal to 0. So LaSalle says that you can only converge to where also theta is equal to 0, not only theta dot is equal to 0. Indeed, there's another solution here. In fact, sine of theta is 0 also where pi is equal to 0. And so the asymptotic stability is certain local, in the sense that you can start from wherever you wish, wherever configuration, with whatever state you have, but you cannot start from theta equal pi and theta dot equal 0, because if you start from there, you will remain there. This is another equilibrium, is the upper equilibrium, in fact. This upper equilibrium, you can imagine, is unstable, because as soon as you perturb it, you will fall down, and you eventually end up with a lower equilibrium. So this is the full analysis. Remember that this slide needs to be corrected. There was an error in the expression of x2 dot, so it's minus b divided ml square, and there's an error in the LaSalle equation theta dot equal minus g0, which should be divided by L times sine of theta. Okay, you will find the correction in the PDF at the end. So this is an example of analysis. There are other stability results. First of all, we can say that what we have said so far holds also for systems that are time dependent, so time varying system, where the right hand side part of the differential equation is an explicit function of t, provided that this dependence is periodic. So if we have that f of x t is equal to f of x of time t plus a certain period tp, and the same is true for the candidate function, the Lyapunov function, then the result that we have mentioned holds also in this case. So why I'm introducing this? Essentially because in regulation task, the reference is constant. But in trajectory tracking task, the reference is a function of time. So we can apply the above results, in particular the sufficient condition of stability and asymptotic stability and LaSalle theorem, also in the case of periodic reference trajectories, which would introduce this time dependence in our closed loop equation. When the trajectories are not periodic, so for general time varying system of the form x dot equal f of x t, which is what we would find when we will face the trajectory tracking control problem, we have additional result. We have a Barbara lemma, which we'll not discuss at this moment. I'm presenting it here. There are some assumptions so that the function, the candidate function, should be a lower bounded function. Its time derivative should be less or equal to 0. Then this implies that there exists the limit of the function v going to infinity, but this limit does not imply the existence of the limit of v dot going to 0. So we need a further assumption that the second derivative is bounded, and this will imply that v dot is equal to 0. This is kind of mysterious at this stage, and we will leave it like this. But if we prove Barbara lemma for our system, and in particular we will show that the Barbara lemma applies to some trajectory tracking controller that we will introduce later on, then the corollary is that we can still use LaSalle theorem as such. Okay, so the Barbara lemma is a lemma in the sense that it allows us to still use not only the Lyapunov condition, but also in particular the LaSalle theorem. So for the time being, we will stay with this. In case we have periodicity of time dependence in our system, we will apply the results that we have seen so far exactly in the same way. Now, let me conclude this first part by mentioning other specific results which are of interest. For instance, what happens if our system is system dynamics is fully linear, so it's represented by x dot equal A times x, with A being a constant matrix. Now you see that the origin, so xe equals 0, is always an equilibrium state for this system, but in general there could be other equilibrium state different from the origin, in particular if the matrix A has not full rank, so it's not it's singular, then all the equilibria will be such that state x that belong to the null space of the matrix A. So for this type of system, no matter if there's only one equilibrium or more, and in particular there is always the origin as equilibrium state, we can have different properties. So we can talk about asymptotic stability, we can talk about global asymptotic stability, we can talk about exponential stability, so the fact that you converge to the equilibrium with a rate which is at least as fast as an exponential with a given lambda. But we have also other property, because we are dealing with matrices. We can talk about eigenvalues of the matrix. So we can say, for instance, that all eigenvalues of A have negative real parts, or that we can solve the so-called Lyapunov equation, which says, which is of the form A transpose P plus P times A, where P is a matrix, equal minus Q, Q is another matrix. And we may have this property that no matter how we choose a positive definite matrix Q in this equation, in this matrix equation, we can find that there exists and is unique a positive definite solution to this Lyapunov equation, and then the function v equal 1/2 x transpose px will be a Lyapunov candidate. Now all these properties, which seems to be independent one of the other, in case of linear system are all equivalent. So for instance, if you have asymptotic stability, this will automatically be a global asymptotic stability. So no matter where you start, you will end up in the equilibrium, which means that there's only equilibrium, and the only equilibrium is necessarily the origin. Another nice result in the linear case is that if you have asymptotic stability, you automatically have exponential stability. Why? Because all the modes of evolution of a linear system are exponential or pseudo-exponential, so oscillating behavior which are enveloped by exponential function. And if those exponentials have negative real parts, if and only if, then you have stability, exponential stability, global exponential stability, and so on. And indeed, you can check this constructively by, in this case, the Lyapunov candidate is one that you can find by solving the Lyapunov equation. So there are many stronger properties for linear system. Unfortunately, our system is not linear, so robot manipulator in the general case have a nonlinear dynamics, but still these properties may be useful. For instance, when we consider the stability of the linear approximation of our system. So consider a variation delta between x and, this is not x0, should be x e, so the equilibrium, and consider the linear approximation of our nonlinear system around this equilibrium. Then, if the linear approximation is asymptotically stable, also, if and only if, in fact, also the original nonlinear system is exponentially stable at the origin. So this will be a local result, which is used to estimate the domain of attraction of our control law, and is also can be used to tune up, for instance, the gain of our controller locally around the desired equilibrium. So let's make a break at this point.